okay? We skipped section 15H, and that was on the second derivative, okay? Now the nice thing is there's really nothing new to learn. It's just when you're taking a second derivative, you find the derivative, and then you take the derivative of that, okay? Now I want to think ahead here a little bit. We know that derivative is rate of change, right? So if we were talking about motion, our derivative would tell us our what?
Slope.
Okay, slope. But in the context of motion, we're talking about
Like velocity.
like velocity, okay? Now, if we're getting the rate of change, the derivative of a derivative, exactly. How is our velocity changing? That's the definition of acceleration.
Two exclamation marks.
There are, okay? Let's look at some notation and then we'll practice with one and then we're going to look at, how this is used in relation to the curve sketch, okay? Here's our derivative, y equals f of x. And I want you to be familiar with, there's a couple of different versions of the notation here. And you should be familiar with all of them, all right? Because they're all used frequently. You guys know that the derivative is dy dx, or we could call it y prime, or you could say it's f prime of x. All right? When we take the second derivative, you'll have this. We're taking the derivative of the derivative. We would say that's d squared y over dx squared. Okay? Or y double prime, f double prime, that's our second derivative, okay? So, be careful with your notation, make sure you know what this little 2 stands for in the notation. That means we're taking a second derivative, okay? Now the cool thing is, we could actually keep going. We could take a third derivative, or a fourth derivative, or a fifth derivative. We could keep going as long as we wanted. With most functions, we'll end up getting down to a constant eventually, and then the derivative is 0. And then if we just keep going, it would be derivative of 0 is 0, so it'll be 0 forever. But if you see another little number, that just means you need to take the third derivative, or fourth derivative, or whatever that is. Do be careful here, put it in parentheses. If like you had y and you were doing the fourth derivative, put the 4 in parentheses so we know it's not y to the 4th power. Okay? But other than that, it's all notation for the derivative.
Why is the 2 between the d and the y, dy dx?
You're taking the derivative twice of y with respect to x twice. It's kind of the idea. Okay? Not super picky about it. I mean, try to do it right, but it's not the kind of thing that anyone's going to bat an eye about if you have the 2 like in front of the x or behind the y or something. Okay? So, that's our idea for second derivative. So let's actually practice this. Let's practice it once with a quadratic, or not a quadratic, a polynomial. All right? So let's say f of x is, let's say, a 5x to the 4th power plus 7x cubed minus 3x plus 4. Okay? So, here's the thing, you're not going to be told to find the derivative and then find the second derivative usually. You'll just be asked to find the second derivative. Find f double prime of x. Okay? So obviously, this is kind of like a recursive process. You have to find the first derivative first before you can find the second derivative. So what's our first derivative?
20x cubed plus 21x squared minus 3.
Very good. Okay? So there's our first derivative. So now we can find the second derivative.
60x squared minus plus 42x.
Exactly. Okay? And that's all there is to it.
Derivatives are so fun.
They are.
Yeah.
Okay? The polynomials are really easy. It can get a little more complicated. But again, this is why we spent so much time with our first derivatives learning how to simplify them. The more you can simplify the first derivative, the easier the second derivative will be. Okay? Now, here's another example. We're doing the tangent of x cubed. Alright, so we need to find the derivative of tangent of x cubed, the second derivative. So the first thing, alright, it's the derivative of tangent is secant squared of x cubed, but we need something else here.
3x
Yeah,
squared.
3x squared.
Good, times a 3x squared. Alright, so 3x squared times secant squared of x cubed.
Do we use the product rule?
Yes, now this is a case where the second derivative actually is getting a little more complicated to do than the first one was. Okay? Does everyone see how we got to this point first
Yeah.
though?
Yeah, but like, did you just know the tangent derivative tangent is secant or like?
Yeah.
Okay.
Yeah, there's not, I mean, technically, since you know sine and cosine, you could do the quotient rule if you forgot, but
Yeah, I was
That's
gonna
just
have to
a-
do the quotient.
Yeah, okay.
that's just a thing, and I'm
So, and what
trying
is
to
the-
remember if it's on the formula sheet.
What is the derivative of secant squared?
Well, for secant squared, you would have to use the chain rule.
Yeah, isn't it?
Because you have something squared, and then you
Okay,
have
what is the derivative of secant?
secant is secant times tangent. Okay?
And then the derivative of negative secant is what?
Well, the negative won't make any difference.
Oh, yeah,
You just
oh,
put
yeah.
a negative in front
So
of.
negative secant times thing.
Mm-hmm. Now, let me, in your formula booklet, they give you sine, cosine, and tangent. Okay? So they tell you derivative of sine is cosine, derivative of cosine is negative sine, and derivative of tangent is. Now, in the formula booklet, they put it as 1 over cosine squared, which you guys know is secant squared. Okay? So you will have those in your formula booklet. If they asked, for instance, for like the derivative of cotangent, you could treat that as tangent to the negative 1 and use the chain rule. Okay? But that's where you're kind of synthesizing what you know about trig with what you know about calculus in order to do the ones that you know. Okay? Unless you just happen to remember that cotangent is a negative cosecant squared. But alright, so now we need to do this. We need to do the second derivative of y with respect to x. Okay? And like we identified, we need to use the product rule. So u is 3x squared, and that means u prime is just a 6x, so that's the easy part. V is a secant squared of x cubed. This one is a little more complicated because we actually have to use the chain rule twice. Okay? What's the outermost function here?
Secant squared of u.
Something squared, right? So, when I'm doing v prime, the derivative of something squared is 2 times that thing to the first power now. Okay? The outermost function is something squared. What's the next function inside?
X cubed.
So be. Oh.
No, 3x
Secant.
squared.
The secant
Oh, okay.
is, it goes, the squared is on the outside, then the secant, the x cubed is on the inside of the secant, right? So, Now we have to do the derivative of the secant of x cubed. Alright, derivative of secant is secant times tangent, okay? I need to move this over a little bit.
Both x cubed.
Yes, because when you're doing the outer function, the inner function stays the same. That's why this stayed a secant of x cubed. It's just to the first power now. Here the x cubed is staying the same because we're just doing the derivative of secant, which is secant times tangent. Then we're to our innermost function times a 3x squared. Okay? So it's got the double chain rule. Alright? So we have here 6x squared. Secant times secant would be a secant squared of x cubed times tangent of x cubed.
Do we have to simplify that further?
Not really. I mean, there's nothing that'll really cancel out here. I mean, theoretically, if you wanted to make secant squared 1 plus tangent squared, you could. And actually, if we were solving this for like, when does this equal 0, you may want to, but at this point we can simplify, or we can leave it like that, okay? Also, remember, we're going to be using this now in the product rule, so we didn't want to simplify too much when we were doing the product rule, because a lot of times we had stuff we could factor out, okay? So now, with our product rule, we have u prime, 6x, times v, secant squared of x cubed, plus u, 3x squared, times v prime, 6x squared, secant squared of x cubed, tangent of x cubed. And here again is why we didn't need to simplify too much, because there's stuff that we can factor out. Okay? We can factor out a secant squared x cubed, we can also factor out a 6x. Okay? So 6x times secant squared of x cubed times, that whole thing was taken out, so it's a 1 plus, and let's look at what's left. What's left here will be a 3x cubed, and then the tangent of x cubed.
But when did the 6 multiply with the 3 of 9? No.
Well, this right here is 18. If we took the 6 out, we'll be left with the 3. Okay? And then you can stop right there. Don't try to, I wouldn't do anything more with that. Okay? Now, that's a more complicated one. Okay? The trig ones usually end up getting more complicated. Polynomial ones typically end up getting a little less complicated. So, it's a little bit of a trade-off.
I remember learning multiplication in first grade.
Oh my gosh.
Remember that was
This
the
is more
hardest
fun.
thing to do.
Yeah.
That was
Who's your other mister?
good old days.
The good old days.
Nick even had to leave because he just disliked your poem.
I think he disliked V prime.
Let's bring it back.
Alright.
memories.
So,
Wow.
here's the thing, guys. One of the biggest things on these is going to be just being careful, neat, and staying organized. Okay? Which I know can be a struggle. But take the time. When you see it's going to be something complicated like this, take the time to write out your u, your v, your u prime, your v prime. Okay? It's worth it. because it'll save you a lot of headaches later. Okay?
Do we need to memorize the? What do you call the derivatives?
It's identity.
Tangent and.
That's on your formula booklet, and actually from now on, you're going to use your formula booklet on any more of the exams I give you in class, and you'll have it on the exam at the end. I had you do everything from memory for our last unit because ideally you want to have as much of this memorized as possible and just use the formula booklet as a fallback. So, but yeah, from now on your unit tests, you'll have the Zob IB test, so we'll go back to using the formula booklet. Okay? So, we talked about, we mentioned already that since the second derivative is the rate of change of the rate of change, you know, this is one application would be, this could be like our position. This could be our velocity.
Is there a third derivative?
Oh wait, hang on. That's not position. Position would be your original y. The derivative is your velocity. The second is your acceleration. Okay? You can do a third derivative, or a fourth derivative, or a fifth derivative. You can go as far as you want.
What would the point
Okay.
be in like?
In terms of this, there's the, I think there's a jolt and a jerk.
Oh, yeah, impulse.
Yeah.
I can't remember which one is which.
The jerk.
Jerk is
Yeah.
the third, and then,
Acceleration.
okay, so an acceleration of acceleration would be a jerk, and then a jolt would be
The
the
acceleration of the
change of that, yeah, so, anyways.
Acceleration of the jerk.
So, but anyways, that's kind of the idea here, and I introduced it early, even before we're getting to applications like this, because it's a concept I want you to really have ingrained in your memories, okay? So, let's talk about what this second derivative tells us about the graph, okay? We've got the concept here of concavity, all right? Concavity. Now, if something is concave downwards, you see something like this, all right? Notice, part of this, it actually, the function is still increasing, but it's concave downward because notice here, we're increasing pretty fast, but here we're increasing a little slower. It's still increasing, but what's happening? If our velocity is slowing down, then our acceleration must be negative. Okay? Our velocity is slowing down when our acceleration is negative. Okay? So we say it's concave down. Here, even though we're going downhill, here we're going downhill fast, but here we're still going downhill, but not quite as fast. So we're actually speeding up from a velocity standpoint. We're getting towards the positive. Okay? And that's one thing that's going to be important to recognize when we're thinking about concavity. All right? It's really easy to try to think of concavity the same way you would think of your velocity, where if we're going down, concave must be down or negative. It's not. It's how is our rate of change changing? Okay? Now, we'll get into more of that and apply it a lot more here in the future, but I want to address this here a little bit more specifically, okay? As we said already, f prime of x is the rate of change of our position, f of x. F double prime of x is the rate of change of the velocity, okay? Hence, we had that concept of acceleration. Okay? Now, Notice here we have this function y equals a negative x squared. Look at what's happening to my slope. What's happening to my slope as I go from left to right?
Decreasing.
It's decreasing, okay? So if my velocity, my slope is decreasing, that means my second derivative has to be,
Negative.
no, it just has to be negative, okay? It has to be negative. Okay? We're not talking about the second derivative increasing or decreasing, because for that we'd have to look at the third derivative. Okay? The fact of the matter is, actually with this function, our second derivative is constant. This has a constant slowing down. And understand this, when we're talking about slowing down, we're talking about our velocity is moving towards the negative direction. Okay? So this is speeding up, this is slowing down, okay? Because we're talking about velocity, not speed, all right? Velocity has direction involved. A positive direct velocity is a velocity that's moving this graph upward. A negative velocity is one that's moving this downward. So our velocity doesn't actually change to a negative until here, where our slopes end up being negative, okay? Positive velocity here, because we're still going uphill, we're still increasing, okay? However, through this whole thing, our velocity is going down. Our velocity is decreasing, so our second derivative, or acceleration, is negative, okay? You think of it kind of like when you've gone down that first hill of a roller coaster. Have all of you ridden a roller coaster before?
Yes.
Okay? You go down that first hill, and then you go up another big hill, okay? It may not be real noticeable on all the rides, but on a lot of them especially, you go up that next big hill, and as you're going super fast when you start into that hill, but as you get towards the top, it slows down, and sometimes it slows down a whole lot. Okay, your acceleration as you go up that hill, gravity's pushing down, and it's slowing you down. You're still going up, but your speed is decreasing. Okay? And that's because you have a negative acceleration. Even though you're going up, the acceleration is going down until finally that negative acceleration overcomes any upward thrust and starts pushing you down the other side of the hill. Okay?
In which case would you be accelerating
Well,
positively?
well, there's a point, okay? Here's the thing. Your speed will be increasing, but your acceleration would still be decreasing. Because the faster you go downward, that's a negative velocity, so your acceleration is making you go faster and faster in the negative direction. Okay, so you still have a negative acceleration. We'll talk about that more, and we'll do some more applications I think will make sense. But for right now, okay, I think we've got enough. Here, this curve is concave upwards, and you'll notice, even though we start with a negative rate of change, what's happening to our first derivative? The slopes here, the derivative, the slopes are increasing. Okay? So that means our acceleration must be positive. Okay? The second derivative is positive. And again, when we're talking about positive, we mean that it's pushing it in the positive direction. Okay? So, I want to just show this to you to introduce a term to you. We're going to do more with this term on Monday. Okay? but obviously there are going to be points, unless you're just dealing with a parabola, where our acceleration is going to be going downward. Our acceleration is going to be negative, but at some point it actually starts going positive. This is like going back to the roller coaster. You go up that hill and you're slowing down, okay? But you've got another hill to go up, right? Okay? There's going to be a point in here somewhere. See it? Okay. There's going to be a point in here somewhere where you stop slowing down, you know, because like the rest of the cars behind you are keeping you from speeding up yet. So you're still slowing down. It's still pushing you in the downward direction. You're speeding up in the downward direction, but then you start to pull out of it. See ya. You too. Okay. You start pulling out of it. And this is where you start to feel those like G-forces pushing you down in your seat, because now it's trying to lift you out of that drop. At that moment is when the acceleration, or your second derivative, was negative, but now your second derivative, not of 0, of x, is now positive, because it's pushing you upward. Even though you're still going down, it has to push you upward in order to slow you down enough to where here you actually start to move upward. Okay? So it's kind of a weird thing to wrap your head around, but that exists anytime you have a change in concavity or a change in curvature. And this point here is what we're going to look more closely at on Monday. But that point, that moment when you stop having a negative acceleration and you start having a positive acceleration, you stop being concave down and you start being concave up, is called a point of inflection. Okay? A point of inflection. If you think about it, if you have inflection in your voice, your voice is going up or going down, it's changing its tone. Okay? It's kind of the same thing. We're changing from our acceleration is changing at that moment. Okay? So, what I wanted to try to do here, I've only given you 3 problems for practice. Here, it's just find the second derivative, and then we're taking it one step further, set that second derivative equal to 0, and try to find those values where it equals 0. Okay? Because we're going to do some sign diagrams. Okay? We're going to do some sign diagrams. It says, consider this function, complete the table. And notice here, we're kind of doing 3 different sign diagrams simultaneously. But they gave you the values that they want you to use. Okay, you're not having to find those values yet. But notice, here it's just position. Here is the f prime of x. Okay? And then here's our second derivative. So find your first and second derivatives, and all you have to do is plug in these values to fill in, is it positive, is it negative? Okay?
I'm just trying to find like the point of inflection.
Well, this is what we will do when we want to find those points of inflection. Okay? So it's just kind of easing you into it. We're not going to worry about the graph today. But I want to use this, and there's another one kind of similar to this where they actually show you, you don't have an actual function, but you're looking at the graph and you're determining, okay, is my position positive? Well, yeah, we're above the x-axis. What about my rate of change? Am I going increasing or decreasing at A?
Decrease.
I'm decreasing, so that'll be a negative. And then, is this a concave up or a concave down at this point A?
Up.
It's concave up, alright, so that's gonna be a positive. Alright? So just try to think through that and do the best you can with that, and then we're gonna use that and relate it to our graph, okay?
Why is D 0?
That's the
Changing.
It's the derivative is zero, right?
Is equal to
It's a
zero.
max point.
It's a max point, it's a critical
So
value.
will B 0 also?
Yeah,
Will what?
B.
B? Yes. Yeah, B will be zero here as well, okay? So, I'm gonna stop this.
So the double derivative